want to talk to you about matter. Matter, by definition, is anything that has mass and takes up space. Now, I know that definition is pretty general, so I want to give you some examples of what is matter and what is not matter. The desk you're sitting at, the air you breathe, and you are all made up of matter. Now, you are not like the air in a lot of ways, but what you do have in common is that you and the air both have matter and you both take up space. Now, some things that are not matter would be energy, light, and heat. Now, heat is a common form of energy that a lot of kids want to say has matter, because you might be able to see heat waves, for example. But all forms of energy, including heat and light, are not matter. So what does matter have in common? All matter have these properties in common: mass, volume, density, weight, and temperature. Now, mass, by definition, is the amount of matter in a substance, and we measure it in grams. Now, a gram is a very small unit of measurement, so if you have a large substance, we might use kilograms, but the standard international unit for mass is grams. We're going to measure mass with a balance. In our classroom, we will use triple beam balances and equal arm balances. Volume is measured in liters, and the definition of volume is the amount of space that an object takes up. A volume is measured in a graduated cylinder, or we can calculate the volume of a regularly shaped object with the formula length times width times height. Now, density is the relationship between mass and volume. The formula is mass divided by volume. The definition for density is how compact the molecules are in a substance. So the more mass I have in an object with a set amount of volume, the more dense it will be. Now, we compare density in terms of sinking or floating. Water is our standard for density that we compare everything else to. Water's density is 1 gram per 1 milliliter of water. So if something has less than 1 gram per milliliter of density, it will float in water. And if it has something greater than 1 gram per milliliter density value, it will sink in the water. Now, weight is measured in newtons because weight is a type of force. The definition for weight is the force of attraction due to gravity. Now, gravity is not in and of itself a force. It is an acceleration. The force that is caused by gravity is weight. Now, the formula is weight equals mass times gravity. Temperature is our fifth property that all matter has in common, and we will either talk about temperature in terms of Celsius or Kelvin. Now, Celsius is what we're going to use for temperature when we measure the temperature, but if we're doing calculations with temperature, we're going to use kelvins because we don't want zeros or negatives in our numbers. Now, there are other properties of matter, like color, shape, and texture, but not all matter have these properties. Not everything has a color. Not everything has a texture. So because these are not true for all matter, we don't have it on our list. these 5 properties are things that are true for anything that's classified as matter. Something else that's true about matter is that it can have a different state. And there are 4 states of matter. We have solid, liquid, gas, and plasma. Now, solid is an object that has set shape and set volume. Now, that word set means that it's not going to change. Your desk is not going to be round today and square tomorrow unless something's happened to it. Now, a solid is the state of matter that has the highest density than all the other states, with the exception of water. You know from personal experience that if you put ice cubes into water, the ice cubes will float. And there is a special reason that that happens with water. But if I were to put a cube of lead into liquid lead, the cube of lead would sink into the liquid lead. So that's all the other states of matter for all the other substances will follow the rule that the solid has the greatest density. Water is the only exception. Now, the molecules inside a solid are moving, but they can't get anywhere. So if you picture an elevator full of people, you can shift from one foot to the other or maybe elbow the person next to you, but you're not going anywhere. So you're all kind of vibrating in one place, wishing that other people would move so that you could move better. Now, a liquid still has a set volume, but it has no set shape. So a fun trick to play on a younger child is to take a can of Coke and pour half of the Coke into a tall, narrow glass and the other half into a short, wide glass, and ask the child which one has more Coke. And they're going to be tempted at a younger age to choose the one that has a taller level for the volume because they don't understand that it's just taken the shape of the glass and the volume has not changed. Now, liquids flow around each other. So if you could picture a swimming pool where, you know, you might have one person swimming across the top of the water and then someone else could swim under them, under the water, and they could flow over or around each other. So these molecules are allowed to flow in and around each other. They're not stuck inside like these people in the elevator. Now, a gas is different from a liquid in that it has no set shape or set formula. So a gas's volume, I think I just said no set formula, no set shape or no set volume. A gas's volume can change because of its temperature or pressure change, and the gas has high energy and low density, and most of the molecules in a gas will behave as if they were separate. They'll be independent of each other, except for occasional collisions. And the way I like to describe a gas is if you could imagine a bunch of 2-year-olds playing on a playground, and they play independently of each other, and every now and then you have a collision, like the kid coming down the slide collides with the kid that's throwing rocks up the slide, and they will collide, but they're not playing together. Now, a plasma has no set shape and no set volume, just like the gas, and it's high energy, like the gas. In fact, it has higher energy than the gas, but the difference is that it has charged particles. So instead of having these independent molecules that are either stuck together, flowing around each other, or colliding into each other occasionally, we're going to have a breakdown of those particles, and we have charged particles that are flowing in and around each other. One of our properties that we talked about was density. So we're going to encounter some density problems in this unit. Here's a density problem. Calculate the density of a clay boat with a mass of 2.5 grams and a volume of 7 milliliters. Our first step is to identify our knowns. So I see that I have 2.5 grams and 7 milliliters. My second step is to label those knowns. What do they measure? Well, grams measures mass and milliliters measures volume. My third step is to check my units to see if I have anything I need to fix. Well, grams is a small measurement of mass and milliliters is a small measurement of liquid volume, so those two work together. If one had been kilograms and the other had been milliliters, I would need to change one of those so it would match the other one. My last step is to substitute and solve. So my formula is density equals mass over volume. The 2.5 grams is my mass, divided by 7 milliliters. So when I divide those two, I get 0.36. Now, grams over milliliters does not cancel. So I would rewrite both of those units in my answer. So a density unit is grams over milliliters. You can have grams over milliliters or kilograms over liters. If we had a regularly shaped object instead of a fluid, like we have here, with the boat being an uneven shape, we are going to calculate it using water displacement. If it had been a regularly shaped object like a cube, we would have centimeters cubed, so it could be grams per centimeter cubed, or we could have meters cubed, which is a larger unit like I would do in a room, so I would have that as kilograms per meters cubed. Now you still have a mathematical triangle here. Mass and volume are dividing, so I put the mass on top, the volume under it, so that they will divide, and the density takes the leftover space. 2.5 divided by 7 will give you the same answer we got here. Temperature can be measured in 3 different scales. We have Fahrenheit, Celsius, and Kelvin. Now Fahrenheit is based off of the English system, and it's what we use in America. But it's not very useful to us in science because there's not an easy relationship from Fahrenheit to Celsius or Kelvin. So you know that water freezes at 32 degrees Fahrenheit, and you know it boils at 212 degrees Fahrenheit, but we are not going to be using Fahrenheit in our classroom. If we are measuring temperature, we will use the Celsius scale. It is based on water's properties. And what that means is that it was set so that 0 degrees Celsius would be freezing and 100 degrees Celsius would be boiling. 0 and 100 are easy to remember, and they're easy to use for quick calculations. So it was purposeful to make a temperature scale that used those values when you're doing measurements. Now, water's properties are used because water is one of the most common substances that we use. But when I put 0 into an equation, or negative temperatures, interesting things will happen. If I multiply a value of volume, for instance, with a temperature of 0, I'm going to say that the volume went to 0 milliliters, and my substance did not just disappear. It got colder, but it did not disappear. So we needed a different temperature scale that took away that 0 problem. And so what we have now is Kelvin. And Kelvin is based on absolute 0, which is 0K. Absolute 0 is a theoretical temperature that we have never reached. And the theory is that if we ever got to 0 Kelvin, matter and energy would cease to exist. So 0K is not okay. That means that it must be much larger than the 0 scale we have here. And if you notice, freezing in Celsius was 0 degrees Celsius. Well, freezing in Kelvin is 273 Kelvin. Boiling in Celsius is 100 degrees Celsius. Well, boiling in Kelvin is 373. If you notice, the difference between these two is an even 273 degrees. So we have a formula that we can use to go from Celsius to Kelvin. If I have Celsius and I want Kelvin, I'm going to add 273. If I have Kelvin and I want Celsius, I will subtract 273.